value of x. If you wanted to know what the limit was for x equals 5, you'd have to redo that process. If you wanted to know what the limit was at x equals negative 10, you'd have to redo that process. So it'd be nice if we had a general way to find the slope. Okay, kind of a general rule for the whole graph. So here's what I'm going to do. Instead of picking a specific point 2, 4 to find the slope at, I'm going to pick a point, and I'll call it x squared. So it's a general point, okay? It's a general point, and I'm calling it x squared, all right? So, you know, just x representing just any value. It could be any number. It could be negative 5, it could be 10, it could be whatever. And x squared I got by plugging x into my function is just x squared. And what I'm going to do, I'm going to pick another point close by, okay, a distance of delta x away. Okay? So I'm picking another point close by, you know, it's probably not exactly how I'm doing this, but it's supposed to be a distance of delta x away. And so that point right there is going to have an x-coordinate of, so, you know, from here to here, that is a distance of x. And this is an additional delta x away, so it will be x plus delta x. And then, how I find my y-coordinate at this point is I take x plus delta x and I plug it into my equation, which is x squared. So I'm taking x plus delta x and replacing it for x. So it's going to be x plus delta x squared. Alright, now what I'm going to do is, so basically I'm trying to find the slope at this point. And I'm using the same idea as before that, you know, here I have a tangent line. I'll just kind of freehand draw this, so it's not very good, I know. That I want to find the slope of that tangent line, and I'm drawing out the slope between these 2 points, and you can see how it's different, and it's probably hard to see what that looks like. But if I bring this point infinitely closer to this other point here, you know, it will end up matching up with the tangent line is the idea, just like the previous example, it's just we're doing a general point. So I'm going to set this up using my slope formula, doing y2 minus y1, so it'll be x plus delta x squared minus x squared all over x2 minus x1, so it'll be x plus delta x minus x. Now I have to think, okay, I need a limit thing going here because I want to bring this infinitely closer. So I have to think, as this point gets closer and closer and closer and closer to this point right here, okay, what's going to happen is this delta x is going to shrink smaller and smaller and smaller. And it, you know, as it approaches that point, so the point gets infinitely closer, delta x will go to 0. So we're going to do the limit as delta x approaches 0. Alright, so how we work this out? You'll notice here that the x's cancel. If you set these up right, it will always cancel. You always just have delta x in the bottom. Okay? Or if you know, I could have done these backwards, doing x squared minus this term, and put a negative delta x, but I always do the delta x first. Okay, and that goes along with the definition of the derivative. So, let's see here. So now what I'm going to do is I'm going to distribute this out. And it's going to end up being x squared plus 2x delta x plus delta x squared minus x squared all over delta x. And if you need to square that out, you know, and take your time, go ahead and do so. But it'll square it to that. I'll notice that I have my x squareds canceling out. You'll always see something like that happening in problems such as this, okay, where you can expand and cancel. And then your remaining term should have a delta x left in it. So I'll factor that delta x out to get a 2x plus delta x all over delta x. Okay, so you can see I factored a delta x out of this term, it left me with a 2x. When I factored delta x out of this term, it left me just with a delta x. So the delta x's cancel out, and at this point now I can plug 0 in for delta x, because all I have left is my 2x plus delta x. And when I plug 0 in for delta x, it just leaves me with 2x. So, what I have figured out is, I have figured out the derivative of y equals x squared. So the derivative of y equals x squared is 2x. Okay? What that means is, I can find the slope of y equals x squared at any place I want, okay, using this as my general rule. So just a second ago, we did x equals 2, okay? So all I would have to do for this now that I know that the derivative of x squared is 2x, is I'd plug 2 in for x, and it would end up being 4. So the slope is 4, just like we said. If I were to know what is the slope at x equals 3, I plug in and I get 6. So that means that the slope of x squared at x equals 3 is 6. If I want to know the slope at negative 5, I plug it in for x, it's a negative 10. Okay, that's what the slope of y equals x squared is at negative 5. It has a slope of negative 10. And on and on. So I could do any value I wanted. I could find any slope I needed to find from that 2x. Okay, so again, this 2x is the derivative of y equals x squared. All right, let's look at one more of these just to try and make sure we're clear with how we find the derivative. So, we just did an x squared problem, okay? And for that one, I had a graph going and everything, but you don't need a graph for all these. I actually like to look at a graph for them, but you don't need it, okay? And what you need, so in the previous one, we started with 2 points. We found 2 points and we made a slope out of those 2 points. So the first point that you always need is your general point in that case. So in the previous one, it was x squared. Well, the x-coordinate will always be x, always, okay? The y-coordinate, though, is going to change depending on our function. So, basically you take x and plug it in, so your y-coordinate for your general point will just end up being what your function is. And then you're going to have your second point that is delta x away. So it's always going to be, the x-coordinate will always be x plus delta x. So you have 2 points, one of the x-coordinates is x, one is x plus delta x. The y-coordinates will vary. The y-coordinate then you get by plugging x plus delta x into x in both of these. So it will be 3 times x plus delta x minus 4 times x plus delta x squared. So again, I took x plus delta x, put it in for x here, put it in for x there. Alright, now what I need to do, I need to make a slope formula out of these. So it's going to be y2 minus y1 . Okay, and then I'm minusing y1, and notice I'll put parentheses around that. Okay, and I'm doing that because I don't want to forget to distribute my negative. Okay, I would definitely miss a sign in that case. And then I'm going to do x2 minus x1 plus delta x minus x. And we take the limit as delta x approaches 0. Sometimes you might see certain books or certain tests or whatever will use h instead of delta x, but it's the same thing. So if you have x plus h here, it would just be 3 times x plus h minus 4 times x plus h. So it's the same thing where you see x or h or delta x. So again, the x's cancel. I'm at the point where I know that they're going to cancel, so I really don't need to write anything, those x's in here. I'll just immediately write the delta x in there. So let me go and distribute here. So I have the limit as delta x approaches 0. I'll distribute to get 3x plus 3 delta x minus 4 times, and I'm going to square that out to be x squared plus 2x delta x plus delta x squared minus, and I'll distribute my negative, 3x plus 4x squared all over delta x. Okay, let me take this up here. And so I still need to distribute my negative 4 right there. So the limit delta x approaches 0 of 3x plus 3 delta x. And I'm sorry that I'm blocking this out, but I've just rewrote that. Now I'm just going to distribute my negative 4. And so it's just going to be negative 4x squared. Distribute it to here is going to be negative 8x delta x minus 4 times that is going to be 4 delta x squared, and then minus 3x plus 4x squared. Hopefully we can see that in the corner there. That's minus 3x plus 4x squared. Okay, so now what I should notice is some things should be canceling. For instance, the 3x here, the minus 3x right here. The minus 4x squared, the 4x squared right there. And as always, the remaining terms will have a delta x in them. When I say as always, it's with these types of problems that are kind of like polynomial type of problems. But if you're dealing with a radical or rational function, it might be different. So it ends up being 3 delta x minus 8. Oh, I'm sorry, let me factor out a delta x out of that. So it'll be delta x times, factor out of that, leaves me with a 3. Factor out of here leaves me with 8x. Factor 1 out of there leaves me with minus 4 delta x. All over delta x. So So the delta x's then cancel. At this point I can plug 0 in for delta x. I'm just left with 3 minus 8x. So I have that the derivative of 3x minus 4x squared is 3 minus 8x. Sometimes you'll see it written like this, and you'll get used to this notation. F prime of x equals 3 minus 8x. F prime is just another way of saying the derivative of f. Okay? So I want to make sure we know what that means, that this is the derivative. So this right here allows us to find the slope of this function at any value of x. So for instance, I can find f prime of 1, which means I just plug 1 into the derivative and I get 3 minus 8 is equal to negative 5. So what that means is, at x equals 1, the slope of this function is negative 5. I could do the same with any other number. I could do that for 10, 20, negative 50, whatever I wanted to, and I could find the slope of this function at any x value I wanted to from this derivative. The derivative is really just a general rule for the slope of that function.